We're going to have a very abbreviated look at the biomechanics of the wrist. That is the arthrokinematics and the conjunct rotation. It's an introductory talk, and you'll be seeing more of this as we go on. The simplest thing in the wrist is flexion and extension. Actually, the wrist isn't difficult anyway, it's just a lot of bones to remember. For flexion and extension, the carpals present a convex surface to the radius ulna and the meniscus. This means that the arthrokinematic, the glide, will be in the opposite direction of the osteokinematic. So during extension, the whole carpal row will glide at the radiocarpal joint palmally, and during flexion it will glide dorsally. It's as simple as that. There will be some movements between the intercarpal joints, which we'll look at it in a little bit with conjunct rotations. But there's not an awful lot of up and down movement or side to side movement at the intercarpal joint because, as we'll see, this is a concavo-convex surface. To be more precise, it's from the radial side, it's concavo-convex, concava again. So you don't get an awful lot of movement there. The surface shapes tend to lock this, so it doesn't have an awful lot of movement available to it. But simply enough, for flexion and extension, dorsal gliding for flexion, palmar gliding for extension. You can see here that the joint line at the intercarpal joint is concavo-convex and actually a little bit concave again. So the traps present a concave surface to the scaphoid. The capitate and triquetrum present a more or less convex surface. So it's a concavo-convex surface. It's only got 1 degree of freedom. It can flex and extend a little bit, but abduction is beyond it as far as primary movements are concerned. You can see they'll lock. I mean, basically, during radial and ulnar deviation, they can't move. If they could, if you're doing radial deviation, for example, the traps would move radially, glide radially, while the capitate and the triquetrum, hamate, would glide ulnarly. They'd have to split in the middle, which they can't do. So radial and ulnar deviation doesn't occur here. During flexion extension, there's this surface allows conjunct movements, which we'll see, and these occur around a midline axis through the capitate and the lunate. But no abduction, no radial and ulnar deviation at this joint. Looking at the conjunct rotation of the wrist, during flexion and extension, you get fanning and folding. It's basically pronation and supination of the wrist. I mean, there's no other way of doing this. It flattens out and it twists. There's no difference between this and the foot when you get right down to it, except this occurs under non-weight-bearing conditions, whereas for the foot it's always weight-bearing. And you can feel this quite clearly. If you palpate the four corners of the carpal tunnel, there's a hook of hamate, the trapezoid ridge, scaphoid tubercle, and the pisiform. During flexion and extension, you'll see that during extension, those four corners spread apart, and during flexion, they come together. So you get this movement occurring. Flexion, you'll get this happening, and extension, this. This is pronation and supination. It's just not called that. Now, you can see from the diagram this a bit more clearly. The four corners fold in. The arch of the tunnel becomes higher, more twisted, with extension, with flexion rather, and with extension it flattens out, and the arch becomes lower. Quite simple, and it's very, very palpable. So essentially that's the biomechanics of the wrist. Not overly complex, just be aware of them when you are testing mobility and mobilizing. Good luck with it.